Okay, so today we're going to talk about predicting using probability and proportions. All right, so we're going to start with some things that are using theoretical probability. So remember, it's kind of overtaped there, so that didn't quite work. But remember that theoretical probability is when you are using math to determine a probability. So, for example, here's an example where you can use the number of squares to determine what the probability is that the treasure is hid in the den. Now there's a total, and remember the probability it's in the den is the total squares in the denominator and the number of squares in the den in the numerator. Okay, so in this case, and this is not a prediction right now, this is just a theoretical probability. The theoretical probability would be 1, 2, 3, 4, 6, 7, 8, 9, 10. So 10 over 100, okay, or 1/10. Okay, so 1 in 10 chance that it's going to be in the den because there's a total of 100 squares. Now, you can make a prediction if we were to play this game randomly and you're randomly going to, how many times would you expect it to be in the den based on it randomly being placed on any one of these squares? So now you're going to set up a proportion because you know the chance of it being in the den is out of those 100 squares, it's 10 times. So out of the 100 squares, it was 10 times. And it's a relatively simple proportion. You're playing the game 200 times. Okay, and how many times would you expect that treasure to be in the den? Because if it's randomly placed, this gets multiplied by 2, and relatively simply, you would expect it to be in there 20 times. Okay, somewhere in the den, 20 times. Okay, so it's a relatively simple idea if the probability is easy. So here are some other examples using a coin flip and a spinner and a number cube. Okay, so if the event is if you flip it 200 times, how many tails do you think you'd have? Well, every time the probability, so the theoretical probability of tails is just 1 time in 2. Okay, so that's 1 time in 2. So how many times would you expect it out of 100? We'll just set up that proportion. 1 out of 2 equals how many out of, 200. Okay. So if you multiply by 100 here, you're going to multiply by 100 here, and you would expect it to happen 100 out of 200 times. So your answer would be 100. Okay, and that's how you would show work. So same thing here. If you spin this spinner 40 times, how many times would you expect it to be a 4? Okay, and these are relatively simple ones. Okay, so the probability of a 4 on this spinner up here is a 1 chance in 5 because they're each the same size, or at least pretend they're exactly the same size. And the 4 happens once. So the probability of a 4, there's a total of 5 options, and 1 time it's a 4. Now, if you spin it 40 times, you're going to now set up a proportion. 1 in 5 equals how many in 40? Okay, and if I multiply by 8 there, I'm going to also multiply by 8 here, so I would get 8 times out of 40. So these are relatively simple ones. We'll try the cube. And if I were to take it 60 times, how many 6s would I have? Well, the probability of 6 on any one roll, there's 6 sides, so it's 1 out of 6. And so 60 times, 1 in 6 gives me how many in 60? And again, this is relatively proportional. I'll just divide this time, so divided by 10. So in this direction, I'm going to multiply by 10. So it'd be 10 in 60. So my answer would be 10. Okay? Now, sometimes they're not quite so simple. They might be, and so I'll use experimental probability to show that, because often experimental probability is going to be a situation where you don't have quite such an easy number of times something has happened where it equals out to be easily proportional. Okay, so here's the data table. This is an experimental probability because I actually rolled a die a long time ago, but I actually did roll a die 30 times. And so predicting based on experimental probability may not be quite so simple. So I rolled it 30 times, okay? And here's how many times it happened in each number. So the 1 happened 6 times, the 2 happened 3, etc. Okay, so if I want to know, let's make it the first one really simple. So the chance, or the number of times we'd get a 3 if it's rolled 90 times. Okay, so let's still make it kind of simple. If it's rolled 90 times, how many times would I get a 3? Well, out of 30 times up here, I got a 3 4 times. So how many would that be in 90? It's a relatively simple idea. I'm going to multiply that by 3, so I would expect it to happen 12 times. So it can be simple whether it's theoretical or experimental probability. But, and I'm just going to sneak this down, if I, let's say I want to know out of 100 times. So, and let's say I'm going to do, I don't know, the 5. Okay, out of 100 times. So this is the slightly different, more difficult situation where it's not a simple probability. It was 5 out of 30. Okay, and how many is that out of 100? But it's still just, or sorry, it's not a simple proportion is what I meant, but it's still just a proportion. So I can still figure out, and in this actual case this can be relatively simple because I multiplied by 6 in this direction, but 100 divided by 6 is not going to come out whole. And you do kind of have to round these. You can't say it's going to happen. So if I divide this by 6 and I say it's going to happen 16.6 times. So it's going to happen 16.6 repeating. So let's round that to around 17 times. Okay? So you're going to round it to the nearest whole number when that happens because you can't have 16.6 repeating number of times A5 shows up. Okay, so, and that's true also in this last example, and it's another experimental probability example. So I know some things about a container. So Jelani's teacher brings in a bucket containing 72 blocks. Some of those blocks are red, some of those blocks are yellow, and some of them are blue. And he wants to figure out how many of the blocks are blue without emptying the bucket. So he draws a block from the bucket, records the color, and then he replaces it. And he does that 14 times. So of those 14 draws, 5 were blue. And now how many are blue based on the experiment? So remember, there's a total of 72 blocks, and we know his experimental probability of blue. So the probability of blue, experimentally, was 5 in 14, right? That's what we know. We also know the actual total. There are 72 blocks. Okay, so we can set up a proportion still here. The problem is the proportion's not so simple. So when I do 72 divided by 14 or 14 divided by 5, depending, if I do 72 divided by 14, I get a really, really, really not so fun number. So let's try 14 divided by 5. That one's a little bit better, 2.8. So if I look in this direction, I know I divided here by 2.8. So I can do that with the 72, but it's still not going to be perfect. Okay, so I'm getting 25.7, So if I divide by 2.8 here, and I get 25.714, okay, I'm going to round that to around 26. That's why you really need to show work on these because it's approximately 26, but you never know. It could be 25. It could be, it could be, to be honest, very different because this experimental probability may be way off since he only drew 14 times. So you're just using the proportion that you have to take a relatively educated guess as to the total. All right, so there's the examples that I have, and I want you to practice, but most of it's really just proportions. Some of it will be finding simple probabilities. Have a lovely Monday or Tuesday. Bye.